It's my great pleasure to introduce our plenary speaker today. Hussein Abbass is a full professor in the School of Engineering and Information Technology in the University of New South Wales in Canberra. He was also working for industry in the IT domain. You certainly know that Hussein Abbass is the founding editor-in-chief of the IEEE Transactions on Artificial Intelligence, which has been launched last year. He's also an associate editor of a number of IEEE journals. His main research is about AI technology, algorithms, and human AI teaming, and he has applied his research to a wide variety of applications. Hussein Abbass is a fellow of IEEE, a fellow of the Australian Computer Society, a fellow of the UK Operations Research Society, and a fellow of the Australian Institute of Managers and Leaders. He'll present a lecture with a provocative title, Artificial Intelligence is Not There Yet. Let's welcome him. Please, Hussein.
Yes, thank you. And thank you for the invite and the introduction. I will just share my screen. Excellent. So thank you for the invite. It's a real pleasure to be here with you today, talking to you about this exciting topic about AI is not there yet. Before I kick it off, I just would like to make a disclaimer that anything that I would be saying today is mainly my own opinion, and it does not reflect any official views of my collaborators or any of funding agency. So just an overview of the talk. I will talk a little bit of history, and I will be talking a little bit about some of the challenges. Then I will give you very quick overview of a very small subset of the topics that I'm working on at the moment, which is mainly machine education. Then I will leave you with some ideas about where the future of AI and some of the challenges in AI are heading, then conclude. And as I was telling Sanaz, I will start slow and I will speed up as I keep going. So what my main question that I am trying to address today is, are we actually close to have true artificial intelligence for complex tasks? And to be able to answer this question, I would like to take you through a few historical encounters going back almost 70 years ago, and focusing on that time frame. And seeing what was said at the time, and I hope that you will be able to contrast what was said in the 40s and 50s to what's happening today in the AI field and where the field as a whole is going. Most of my talk will be based on these three main papers, but I will also be relying on many of our publications towards the end of the talk. And in each slide, you will see at the bottom of the slide some of the papers which are supporting the materials of the slide. So let us kick it off. Back in 1944, the first computer, the British Colossus, and followed by 1945, the American ENIAC. At the time, computers did not have memories. So computers was actually a human job. And the word computer came from this particular human job, which was actually a very specialized field, mainly done by females, required people who are quite clever, who can to do arithmetic and mathematics really, really quickly. And the first design were mainly a translation of that. They did not have any memory. It was just a big mechanical calculator that required hand configuration by the human. So it was a real example of human machine collaboration. The human configure the machine, and the machine performs the task that the human dictate to it. But that all has changed with Alan Turing design of the ACE, or the automatic computing engine. And what Turing did was really magnificent, because he did not just design a new type of calculus, and he did not just design the mathematics of this new computer, but he also designed the circuits. So he went and he did a complete design from the mathematical level all the way down to the implementation. And what Turing did at the time was to introduce this idea of having memory in a computer. And that changed the whole perspective about computers and computer science in general. John von Neumann listened to, he became aware of Turing work, and he listened to some of his talk. And John von Neumann was also inspired with Alan Turing work. And from that, he designed his own computer, which is the EDVAC, the Electronic Discrete Variable Computer. But John von Neumann had a different philosophy from Alan Turing. While Alan Turing focused on the logic, so he designed pretty much computers that require the logic, and he focused on the complex programs and the software and the algorithmic side. John von Neumann focused on designing complex machines, and he focused on the machine itself. So memory is somehow attributed to Alan Turing, whereas what we know today as the central processing unit, or the CPU, was attributed to John von Neumann architecture. Now, I want you to keep this in mind as we start going in history. Despite that these two pioneers designed the first two digital computers, their design was not translated into actual computer. And the first actual computer that was designed was the Manchester baby on the 21st of June, 1948. And the Manchester baby had up to 17 instructions. So Alan Turing was really laughing at that because 17 instructions for him was like far away from his ambitious design. But companies and universities took this design. 1949 saw lots of new different implementation of digital computers from EDSAC in Cambridge, PNAC, and even in Australia. Our Commonwealth Science and Organization, CSIRO, designed the CSIR MIC-1 computer. And the story continued until only 1952, when EDVAC was implemented. Now, remember what I said, Alan Turing actually designed the mathematics as well as the circuits and the whole computer. Von Neumann didn't do that. Von Neumann just designed the mathematics, but it was engineers who actually took his design and transformed it into a real implementation in 1952. Many people saw what Turing did as a complicated machine that was quite expensive. And the first realization of ACE was just a pilot model induced in 1955. And that was followed in 1954 with the G15, which was considered as the first BC or personal computer. Now, you can see with the history of computer came lots of expectations from the community, and you can see on the side one of the newspaper articles in the Daily Telegraph in 1946, written to make radio brain. That was followed by lots of expectation. And in 1950, there was in the Daily Telegraph an article about Alan Turing computer, and it was claimed that might be the fastest brain. And I want you to pay attention to some of these keywords, because that is the time that the birth of artificial intelligence, the true foundation of artificial intelligence, really happened, and talking about these intelligent machines. That was followed by another article in the Times in 1950, talking about the advantage of these computing machines, which can save significant amount of time. And you can see that from very early days, the idea that the computer is going to take over some of the human jobs was quite obvious. Now, to summarize this stage of history, Alan Turing was almost obsessed with speed and memory, and that became the foundation for computational complexity. And when we talk about time complexity and space complexity, that's very much consistent with Turing thinking. Von Neumann, on the other hand, was really obsessed with complex machines and the design of the machine itself. Now, let us look at what was the implication for that on artificial intelligence. And Alan Turing, at the same time, while he was waiting for his dream machine for someone to take and really implement and bring it to existence, he switched his thinking about writing about the computing field and some of the philosophy of that. And one of his most famous articles was The Intelligent Machinery in 1948. And I wanted to see the language change in Alan Turing language. So he opened this article by saying, I propose to investigate the question as to whether it is possible for machinery to show intelligent behavior. All what he was talking about at the time is machines that are able to display a level of intelligence. But it did not take much time for Alan Turing to grow his ambition. And within 2 years, he published a paper in The Mind where his opening statement was significantly different. I propose to consider the question, can machines think? Moving from displaying intelligence into actually a machine with the capacity to be intelligent. We are talking about something in 1950. Now, at the time, as all of these expectations started to grow, people concerns about the possibility of creating intelligence in a machine equally started to grow. So in his 1948 paper, Alan Turing tried to address some of the concerns in the society, and he addressed 5 concerns. The first concern was what I would call the human ego, that humans dominate intellectual power. So how it comes that a machine will dominate and share with humans these intellectual power. The second concern that people had at the time was on the religion side, that the creation of intelligence that could touch on religion side. Now, in his paper, Alan Turing did not spend the time to defend these two. He labeled them as emotional reaction from the public. And because they are emotional, he did not see the point of investing time in arguing against these two. But he spent a lot of time in his article to defend the remaining 3. One a challenge with intelligence was a finite memory, and he thought his ACE machine design is going to overcome that. We are talking about 1950s, very small memories. Look at the memories that we have today. This concern of memory has always been there from the very early days of computing. The second concern that Alan Turing spent actually some time to even do some theoretical studies in is Gödel theorem. And the fact is that the halting problem, the fact is that computer can enter into an infinite loop. So there will be situation where the computer will have no answer. And what Alan Turing starts suggesting is maybe instead of not having an answer, why don't we make computer make mistakes? But will human accept computers making mistakes? And that will come in the following slide with a little bit more explanation on this point. And the last concern in the public was really more of a philosophical one. Who should be getting the credit, the student or the teacher? So if a computer end up to be truly intelligent, was this going to be a credit for the human designer who actually designed this computer to make it intelligent, or the credit should go to the machine which became intelligent? And that is really more of a philosophical perspective. Should the student get the credit, or should the teacher who taught these students get the credit? Now, I would like to move in some of the work in Alan Turing, which touches on our community in computational intelligence. And as a matter of fact, even the definition of intelligence from Alan Turing was relying on the fact that he was talking about generate and test algorithms or heuristics. So he emphasized from the beginning the need of having heuristics to create intelligence. And you can see in this extract from his lecture on ACE in 1947, he said, I would say that fair play must be given to the machine instead of it sometimes giving no answer. So that's Gödel theorem and the halting problem. Instead, he said, we could arrange that the machine gives some occasional wrong answer. But the human mathematician would likewise make blunders when trying out new techniques. What he's saying is human mathematicians, when they are trying to make mathematical proofs, they do make mistakes as well. And mistakes is part of the journey for creativity. However, but the machine would probably be allowed no mercy. So if the machine is going to make mistakes, humans are not going to forgive the machines for the mistake it is going to make. And the ideas from Alan Turing continued one after the other, talking about machines that can solve a problem by searching a space of possible solution. And that's what we do in our community when we talk about genetic algorithms and genetic programming and all of these areas. And in his 1947 lecture on ACE, he actually gave the first definition of machine learning. So he said, we want a machine that can learn from experience. And for people who are familiar with Mitchell's definition of machine learning, that machine learning is the ability of the machine to improve its performance based on experience. The origin of this definition goes back all the way back to 1947 to Alan Turing lecture. Then he also talked about artificial life, and he talked about the machine ability to alter its own instruction as an indication of self-replication as well as learning. The other thing that Alan Turing did in his 1948 paper, he talked about ACE as the organized machine, but he also introduced three types of machines in his paper that he called unorganized machines: the A type, the B type, and the P type. And if you look at the last two, the B and the P, the B-type unorganized machine was actually equivalent to or similar to the perceptron. And initially, Alan Turing claimed that this is universal machine, but this claim was not valid, and he came back and he substantiated that with some assumptions to make his machines also universal machine. That was at the same time that perceptron was actually invented. But what was also interesting is his last type of unorganized machine, which is a P-type machine that he took the pleasure pain systems. And that was the first reinforcement learning idea in the literature of computer science and computing. So I hope that you get to see that many of the foundations of our field, whether we are talking about genetic algorithms, neural networks, reinforcement learning, and really much more artificial life, and so on, they had roots in the very early work of Alan Turing and some of his philosophical discussion at the time. I have to say that not everyone agreed with his perspectives, and some people actually labeled his perspective as unscientific, but nevertheless, it was only a matter of time for our field of artificial intelligence and computational intelligence to evolve to the level to show that his ideas became the science of AI. And his implementation of the Bombi machine, and that is the machine that provoked the Enigma code, he implemented generate and test algorithm. So that was really the first well-known life example of human AI teaming. What the machine was doing, it was generating hypotheses about the possible keys to break the German Enigma machine, and the human takes this hypothesis and try it on the Enigma machine that they had to see if these hypotheses are going to work. So that was the first implementation of human AI teaming and using some of the algorithmic principles that we have in computational intelligence. Then we start seeing AI being implemented in computer games by Arthur Samuel Checker in 1952, and even his implementation of machine learning in his game in 1955. Then there was the real milestone in the field of artificial intelligence with this paper that was published in the famous workshop. And what Newell, Simon, and Shaw did, they used heuristics to mathematically prove 38 out of the 52 theorems in the second chapter of Principia Mathematica book. And on top of that, one of the proofs that the computer came up with was shorter than the proof that was available in the book. And that was the first human competitive results that was generated by AI. And this paper was presented in the famous Dartmouth workshop in 1956, which is considered by many people as the official birth of artificial intelligence. But I hope by now I have convinced you that there is a long history from Alan Turing that demonstrate the implementation of AI. So let us now summarize that time frame. If we go back to what I was talking about with Alan Turing and John von Neumann, one of them seemed to actually be focusing more on the logic, and the other was more focusing on the machine and the control. And this idea became a very influential idea in the field of artificial intelligence. So in symbolic artificial intelligence, when we are talking about prolog or programming and logic, the whole principle of programming and logic is to separate logic from control. So the programmer need to focus on the logic, and they don't get mixed with the control as we do in classic functional programming. And ideas like heuristics and the debate between completeness and incompleteness existed from the first day of the inception of the digital computer. Then obviously things started changing in recent times, and you can see on this diagram why things has started to change. Going back to the main problem that Alan Turing was addressing in his early paper about computer memory, CPU and memory plays a significant role. And in the last decade, we see a very significant change in the landscape of artificial intelligence due to the advancement that happened in the computational power that existed in the last decade or two. And that also had a huge implication on our field. A significant number of papers, growth on AI, significant demand on people with AI skills internationally, moving to the amount of investment in AI. Almost all of that started changing in an exponential rate in the international landscape, and all the way to today, where pretty much there's no industry that has not acknowledged the advantage of tapping into AI in its business. So today, artificial intelligence is still, from a basic foundational perspective, we are still talking about having an AI to understand the world, to be able to predict, to be able to make decisions and control, and to be able to interact. And that is associated with some of the classics from semantics, ontology, to ability to predict with things like machine learning, neural network, genetic programming, classifier systems, fuzzy rule-based systems. All of our technology taps into each of these dimensions, and looking at planning and decision-making, as well as communication and interaction and natural language processing. And you get to see that in this space, the three key technologies, representation as one of the foundational elements of any implementation of AI, has consistently been a hot topic in the AI field. Machine learning and the technologies that we have in computational intelligence as really the most successful machine learning technologies today. You will get to see it in our field of computational intelligence, whether we are talking about neural network, deep learning, fuzzy system, and evolutionary computation, play a significant role in planning and optimization. And that all goes back to the time of Alan Turing, when he was talking about heuristics and some of the initial algorithmic design that Turing had. So what should we call it? Should we call it artificial intelligence? That was, the Dartmouth workshop. Machine intelligence is more appropriate. That's almost like what Turing was talking about, intelligent machinery. Should we talk about it as computational intelligence? I think we need to focus on the substance and leave some of this general semantics out. Whatever we call it, they underneath all of these three fields, we have the same technologies that is making difference in our world today. So we talk about neural network, call it machine intelligence, call it artificial intelligence, call it computational intelligence. It does not make a difference, and it does not change the fact that this type of technology is making significant change in our world today. So that was a glimpse, a very, very quick glimpse of some of the historical foundations of artificial intelligence, and even many of the technologies that we have in our computational intelligence field. Now, what I would like to do in 5-10 minutes is to show you some of our work in machine education. Before I conclude with some of the challenges that I promised you in the beginning, some of the challenges that existed from the time of Alan Turing to today, that we haven't solved them properly yet. So, what is machine education? It's no surprise. Some people, when I talk about machine education, we are talking about taking robots and artificial intelligence to the university. They think that this is like a very futuristic idea, and this idea sounded crazy. But I would like to tell you something which maybe most of the audience have never noticed it before. Machine education was actually mentioned in 1948 paper by Alan Turing. He had a section in his paper called Education of Machinery. But he said at the end of this section, I'm not going to spend the time on that topic because the technology was not ready for what he was talking about at the time. And what you see on the slide now is an extract of his of what he said in this paper. If we are trying to produce an intelligent machine and are following the human model as closely as we can, we should begin with a machine with very little capacity to carry out elaborate operations or to react in a disciplined manner to orders. Then, by applying appropriate interference, mimicking education, we should hope to modify the machine until it could be relied on to produce definite reactions to certain commands. This would be the beginning of the process. I will not attempt to follow it further now. And that was the end of this section. It was a whole section in his paper, almost 1 page, a little bit more than 1 page, and he ended it like that. I will not attempt to follow it further now. So what we are doing in machine education had its roots almost 80 or 90 years ago in Alan Turing work, but we've taken this now to a much higher level because we have the technology today. Machine education transforms AI from algorithms to cognitive agents. And I will be touching on that a little bit now because machine education is a whole talk in its own right, but I wanted to give you a glimpse of this exciting development in AI that is going to change the AI landscape, going from machine learning to machine teaching and curriculum design to now we are actually talking about machine education, putting AI in universities. So before I talk about machine education, it's really important also to talk about distributed cognition. And that is a whole set of branches in artificial intelligence, talking about distributed problem solving, like what we do with our swarm optimization algorithms, like particle swarm optimization and colony optimization. That's all falling under distributed problem solving. There's also the multi-agent system literature, which is a whole field of AI in its own right. But there's also the cognitive architecture, and one of the cognitive architectures that we introduced in the literature is based on Minsky Society of Minds. So Minsky is Marvin Minsky is a cognitive scientist, and his Society of Minds is a very famous theory in cognition, and we took this and we implemented it as a cognitive architecture for AI in our research. So we get now to machine education. It is a distributed AI system. But what's important about machine education is that it is a true collaboration between human and AI. So we are using human as the educators. And over time, we are moving up the level of automation from having autonomous machine learning to autonomous educators and autonomous students. So in machine education, we are talking about how we can actually systematically educate an AI. So not just on an algorithmic level, but designing the level of skill required by the AI, and even giving the AI an exam at the end, how we design these exams for the AI, and how we can certify in the same way we graduate our engineers from the university, how we can actually do the same for artificial intelligence, and how we can actually graduate an AI from our to be university. So that's my dream, to open a university for artificial intelligence. And I'm more than happy to collaborate with anyone who would like to share this dream. And the good thing about that, it's a very multidisciplinary area. We have people from education, from cognitive sciences. We have people who are mathematicians, from artificial intelligence and computer scientists. It's a very much multidisciplinary field. So one of the main problems that I'm solving in my lab is shepherding, and that's looking at inspiration from nature when you look at how dogs collect sheep. Except in our case, while we are dealing with biological sheep, sometimes our dogs could be autonomous systems, and our sheep could equally be autonomous systems. But when you start looking at this problem, you get to see the distributed cognition and the distributed AI. Each of these dogs and each of these sheep are cognitive agents. So we are looking at the cognitive architecture that need to be sitting within each of these cognitive agents, and how we can actually get a machine even on the level of a sheepdog that is clever enough to be able to autonomously collect the sheep without interference from the human. Maybe just with a little bit of guidance from the human, but without getting into deep into how the machine works. Now, that takes us back in time. We've been working on that for a while, and we started publishing on that recently, looking at the human education literature and looking at some of the existing human education literature, looking at how we design curriculum for human and how we can transform that into curriculum for AI. So that's one of our paper in 2019 was actually at IGCNN, which is laying out step by step how we actually design curriculum for an AI. I will not have time to talk about this paper, but I will just show you that we are talking not just about algorithmic design, but we're also looking at understanding the skill set required by the AI and how we can actually transform this skill set and decompose it into sub-skills, and how we go from this high-level description of the skill needed by the AI into low-level description, so that we are able to actually engineer and design the technology and the neural network, for example, that is able to achieve the objective. And we demonstrated with our curriculum approach that there are significant advantages if we do it properly in designing these type of curriculums. Now, I will spend very quickly 2 minutes to show you some of the most sophisticated dimensions of machine education. So the devil is in the details. To design an artificial intelligence that can go to university, there's much more than just designing an algorithm. So obviously, transparency is a big issue. And in our paper, in the philosophical transaction of the real society, we started laying out the calculus required for explainable artificial intelligence, interpretable artificial intelligence and the problem of predictability and mutual predictability between the AI and the human. So if you are interested in that, more than happy to talk to you about it offline, but you get to see how our block diagrams are actually building these AIs that are explainable and are able to also communicate with the human in a meaningful manner. And to be able to do that, we need to look at ontology, which is a whole branch in AI that maybe in our computational intelligence community is not that popular, but that is a very well established field in its own right. And if we would like to design this explainable AI, we had to tap into this ontology and linking it to our computational intelligence technology in lots of different levels. And obviously, we are not really interested just to talk about that and design the calculus. We are interested to really implement that. So we start looking at implementing it in high fidelity simulation, and we take this to some actual robotic implementation, and we take this to the field, and this is our evolving research at the moment, where instead of having a dog, a biological dog, we have a UAV, and trying to get the UAV to collect the sheep on the ground. So, and that touches on many dimensions in artificial intelligence that we don't even cover in our field. So today we talk a lot about human ethics, but also this touches on animal ethics and other dimensions which are quite significant. So that brings us to the end of my presentation, and I promised you to talk to you a little bit about some of the challenges at the end. Some of the lessons learned from the quick coverage of the history that I gave you today. Mistakes should be allowed in AI. I'm not saying that the AI should just go and do random mistakes with catastrophic consequences. What I'm saying is that we know as educators that mistakes are very important for learning, and we've been designing ways to allow the AI to make mistakes without having significant consequences in the environment. We talk about them as safety net. So we design the AI, allow it to make mistakes, but these mistakes are not going to actually have consequences because there is a safety net that will stop these mistakes from getting executed in the actual environment. So we have ways to solve the mistake problems that Alan Turing was talking about in a very safe way. We also talk about heuristics in our field of computational intelligence, and that's that's a topic familiar to all of us. Distributed cognition is something that we have a long way to go in distributed cognition, and attached to the idea of distributed cognition is the idea of distributed understanding, distributed contextual awareness, how we can get multiple AIs who are distributed in the environment to understand what's happening in that environment. And the list of problems for the future of AI is really a growing list. It would be no surprise to see that we need to solve problems about explainability, predictability, and interpretability, but also there are challenges which are sitting at the communication between the human and the AI, and the challenges that I mentioned today about the human education and the AI education. In addition to all of our social integration problems, ethics, legal dimension, and trust. And the last set of challenges is if we are going to take this AI to the real world, we need to actually guarantee that this AI is going to operate in a safe manner. So certification, trust, legality of the consequences of actions from artificial intelligence, ethics assurance, and the whole social integration problem. We've been working across this dimension, but the challenge is huge in this space that require really significant advancement in the field. So my three take-home message for you today: advancing AI need to move beyond the machine learning and machine teaching. We need to start looking at the whole of system design. And AI is not just a single algorithm, it's a whole of system. And we need to start looking at the overall system design. We need to start looking at this machine education, moving beyond the classic machine learning and machine teaching into actually machine education. It was mentioned by Alan Turing 80 years ago, and we've taken significant steps to establish the foundation for this field. But we have also a lot of challenges that many people could tap into. Machine education also brings the dimension of ethics and the legal constraint and the transparency. So, and how to assure artificial intelligence is a big challenge. So my last slide is, my second last is to acknowledge my collaborators. There are many of them, so I wouldn't be able to list them all on a single slide, and my funding agencies, as well as I would like to invite you to some papers to the IEEE transaction on artificial intelligence. This journal has been exponentially growing with significant success, and anyone who is working in the artificial intelligence field, I always say that you wouldn't be working in AI without a paper in this transaction. I have not published in this transaction because I have not submitted, because as the editor-in-chief, I have seen this to be a conflict of interest. But if I wasn't the editor-in-chief, I would have sent my paper there. So I hope the community contribute more to this transaction, because it's only with your help that the transaction will advance. And with that, I thank you for your patience, and I hope to answer any question that you may have. If not now, I am more than happy to do it offline. Thank you.
Thank you, Hussein, for this brilliant talk. I'm sure that we will have many questions. It's so exciting to hear you. And you are welcome. If you want to ask questions, please raise your hand or ask questions in the chat. Any questions?
Looks like there's a question in the chat already from Keely.
Keely, you want to ask your question?
Thank you so much. It was beyond expectation, that talk, so thank you so much. But I'm going to ask a question because I'm sure, as Bernadette said, there's going to be many. So there was many things on there, but one question for today is, you described the need for an ontology. And I just wondered, I've worked with ontologies for several years. How did you develop one so complex for this kind of problem? And follow-on question to that is, can you see this approach being used in other areas listed in the future of AI?
Maybe I would answer the first one, the second one first, if I may, because the first one is a long answer. So yes, I think ontology will somehow find its way in almost every application in AI. If we are going to talk about human AI interaction, and if we are going to talk about transparent AI to the human, I see it quite difficult to imagine such an AI without an ontology sitting underneath it that can guide the interaction of the AI and even guide its algorithmic implementation. How to develop the ontology? There are lots of different methodologies to do that in the literature. As you would be aware, We followed a few of these methodologies. So in our early days, we started looking at, for example, with sheepdogs, we looked at sheepdog trials. And these were very well documented in the literature. There was significant documentation about how to train sheepdogs, and we leveraged this domain knowledge and we extracted our ontology from it. Some of my students at the moment are looking at different ways of upgrading this ontology by involving human experts, by doing some sort of qualitative research and qualitative data gathering. Then after that, you take it to whatever implementation, cottage or whatever, to check consistency of the ontologies and so on. So all the way to some of the symbolic implementation of the heuristics and coupling them with the ontology. And then after that, all the way to our deep neural networks, how to integrate that with our ontology is another dimension of our work. So ontology is likely to be a core foundational element if we would like to trust the AI and if we would like to interact with an AI in a meaningful manner in a social system.
Thank you so much. It's just a brilliant idea. And when you think about it, it's so obvious. So thank you very, very much.
Thank you. I think that Uzai has a question. Uzai, do you want to ask your question?
Okay, can you hear me now?
Yes.
Yes.
Yeah. So yeah, very interesting talk, Hussein. So I'm wondering, when you say, you know, AI as a whole of system design, where do you place the contributions of Norbert Wiener with his cybernetics and also Herbert Simon in this context, because you haven't touched upon their work?
Yeah, I mean, there are so many pioneers in this area, as you know, and you know, Simon is almost considered like the father of cybernetic and management science as well. So, look, it's really difficult to separate cybernetics from what we are talking about here, because whether we are talking about you know, AI from an algorithmic perspective, or we are talking about the human machine integration problem, or the implementation of the AI even on the robotics. So when you look at, I think the best example would be our transaction on AI. Just look at who are the sponsor for this transaction, and that in itself is a demonstration that we can't really separate these fields from each other. The Computational Intelligence Society is bringing, you know, the core AI technology. The System and Cybernetics Society is bringing the cybernetic, is bringing the systems, is bringing the human, the cognitive engineering and the human factor. The Robotics Society is bringing the automation and the control and the implementation. The Signal Processing Society is obviously bringing, and the Computer Society is foundational in that. So it's extremely difficult to separate these fields from each other. I only had a very limited time to focus on Alan Turing because I felt that Alan Turing has not been talked about enough in our community, despite that many of our technology could be contributed to some of the early works that he was doing. And it was truly pioneering at the time, and it is still pioneering to now. So I hope I answered your question.
Absolutely, thank you.
Thank you. There is a question from Mona. Mona, do you want to ask your question? Mona?
Hello.
Yes.
Can you hear me?
Please ask your question.
Thank you for the presentation. My question is, what is the outcomes of the university AI, and how do you evaluate the outcomes?
Thank you, Mona. That's a very interesting question, and it's a really important one. So why are we talking about the University of AI? Because I would like to establish with confidence that this AI has the skills that I have taught it. In the same way, if you think about the outcome of engineer or psychologist or social scientist from our human university, what is the outcome of that? We certify, we accredit the curriculum of the engineer. We have the IEEE, the Institute of Electrical and Electronic Engineering. We have, in Australia, we have Engineering Australia. This professional society come and accredit the curriculum to say, if you graduate a human with the following skills, this human need to have the following skills, and we accredit your degree that you graduate will have the corresponding skills. In the same way, I would like to be able to graduate an AI with a similar accreditation program to what we have in our human university. But on top of that, we don't just teach our engineer the technical side. We teach them how to collaborate with human. We teach them the ethical side. We teach them that engineering is a profession. And these are part of the skills that the ethical dimension, the socio-technical dimension that we teach in our engineer. In the same way, I would like our AI to graduate with a similar skills. Now, that's a little bit ambitious, but we already have hundreds of years of history in human education that we can actually leverage. And we are collaborating with experts in human education to bring this literature to the AI field so that we are able to graduate AI with these skills. How do I evaluate the outcome? I evaluate the outcome in the same way I evaluate an engineering graduate. We have summative assessment that are needed, and different type of test and evaluation so exams and potentially scenarios and context that we can expose the AI to make sure that this AI has accumulated the correct skills for the task at hand.
Thank you. Maybe a final question from an anonymous participant. Can you mention an example system, if there are any, that demonstrates the current best practice of machine education?
Thank you very much.
Can you hear me now? Can you hear me now?
Yes.
Yes.
Hi. Oh, sorry. I don't know. This is a random character. My name is Gus Eiben from Amsterdam. Thank you, Abbass. Extremely nice talk, very motivating.
Thank you.
I enjoyed it a lot. And I would like to motivate my colleagues in this scenario by a good example. So what example could I tell them that you could tell us now about the best practice of machine education, the best we could do today?
Yeah, thank you very much. We have a few papers about that, and if you send me an email, I would love to send you some of the paper. We have the paper that was recently published in the Philosophical Transaction, but we also have a paper is exactly about these principles of machine education that was accepted in the TAIL conference, which is, I believe, Education Technology, IEEE Education Technology Conference, which is talking about a number of principles for machine education. The examples that we use in my group is shepherding. We have demonstrated on a small scale how we can actually educate an AI for this problem. But these are early days, so the examples that we have, are not a fully autonomous system that can go and do things. That is the ambition, but the examples that we have at the moment are sitting on a small scale. We also have a paper that was accepted. I believe it appeared in the early in the early online section in the Journal of Swarm Intelligence a couple of weeks ago. And that paper shows step by step one of the methodologies that we have for machine education for human swarm teaming, and for a particular type of a swarm counting problem, some sort of distributed decision making and distributed consensus approach for that problem. So we have a few examples. Early days, quite small, but they demonstrate the concept. And we also have a number of papers sitting on the methodology, the philosophy, the principles, and guidelines for people how they can implement machine education. And in addition to that, we are always happy to collaborate with anyone who's interested in this topic. We can share lots of the knowledge we've accumulated over many years in that domain.
Thank you very much.
Okay. So we have to close the session now. So thank you again, Hussein, for this very brilliant and inspiring talk. It was really great to hear you. Thank you very much.
Thank you very much for the invitation.
Absolutely brilliant. Thank you.